Hello everyone. Today we're going to talk about exponential growth and decay. We're going to start talking about how it applies to calculus, and then we're going to solve some problems. Problems that we really could have probably solved in pre-calc, but still apply to calculus. So, the number of bighorn sheep in a population increases at a rate that is proportional to the number of sheep present, at least for a while, and we'll talk about that next time. Basically, the population changes based on some rate, and not based on the time, but based on the number of sheep there already are. Okay? Exponential growth means that the more you have, the more growth you will have. It's like interest in the bank. The more money you have in the bank, the faster it'll grow. So let's solve this using calculus. This is a differential equation. I want to solve it for y equals. So I'm going to separate my variables. I'm going to move the 1 over y over here. The k stays here, and the dt goes there. Now I'm going to integrate both sides. The antiderivative of 1 over y is the natural log of y. K is just a number, so if I integrate a number with respect to dt, so this will be kt, and I'll have plus c because I need the constant out there. Okay? I'm going to raise both sides to the e power, or e to both sides. The e and the natural log will cancel out here. I'm going to move the plus c like I normally would, make it e to the c times e to the kt. E to the c is just another constant. So I'm going to rewrite this, instead of e to the c, I'm going to rewrite it as a, where a is the initial value, which makes sense. If you were to plug in 0 for time, this entire thing becomes 1, so the initial amount at time 0 equals e to the c. So what does that leave us? That leaves us with this equation that you're probably familiar with. This y amount is the final amount. This y naught is the initial amount. The k is the growth rate or the decay rate. Sometimes you'll see it as positive or negative in different formulas. I like to just leave it as k, where k could be positive or k could be negative, and t is time. Okay? So, let's try a problem. The population of a bacteria is 400 after 2 hours. After 6 hours, the population is 25,600. How many bacteria were there originally? So, the question that I'm really being asked is why not? Why initial? I don't have the growth rate. And we know it's growing because the population is getting bigger. I went ahead and did all of the arithmetic ahead of time. As you can see, this is going to be very, very arithmetic driven. I'm going to do some of this on the calculator, but sometimes I'm just going to tell you the answer. So let's start off with our formula. The final amount equals the initial amount, e to the rate times the time. So let's fill in two things we know. 400 after 2 hours. So I ended up with 400 after 2 hours, but I still don't know what I started with. 6 hours and 25,600. So 25,600, I still don't know what I started with, and I still don't know what I'm growing by, but I know my time is 6. I have two equations that I can't solve because they have two variables. But if you have two equations and two variables, you can solve them. I'm going to solve both of these for y initial, y naught. So this one becomes y naught equals 400 over e to the 2k. The bottom one becomes 25,600 over e to the 6k. So I still don't know either of my two variables, but I know they're both equal to y naught, so let's set these two things equal to each other. So I have 400 over e to the 2k equals 25,600 over e to the 6k. When we cross multiply, we get 400 e to the 6k equals 25,600 e to the 2k. Two steps of algebra here. I'm going to divide the 400 over here, and 25,600 divided by 400 is 64. I'm going to divide the e to the 2k over here. I have e to the 6k over e to the 2k, e to the 6k over e to the 2k. But when I divide, I subtract my exponents. So 6k minus 2k, I can just write that as e to the 4k. I need to cancel out the e, so I'm going to take the natural log of both sides. The natural log of e to the 4k is just 4k. The natural log of 64, I'm just going to leave as the natural log of 64. Solve for k. I get natural log of 64 over 4. And you can turn that into a decimal if you'd like, but that will give you a less exact answer. This doesn't answer the question. The original question asked, how many bacteria were there originally? Well, I have two different equations I could plug this into. I'm going to go ahead and plug it into the easier one, the smaller numbers. Y naught equals 400 over e to the 2k. So the original equation was y naught equals 400 over e to the 2k. I know that k is natural log of 64 over 4. Let's use our calculator to type this in. The calculator can take care of all of these ugly fractions for you. Alpha y equals 1 puts a fraction bar in the problem. So I'll do 400 on top. E to the 2 times, parentheses, I need another fraction bar, natural log of 64 over 4. Now I realize there are other ways to write this so that you don't need the fractions. You could rewrite them as division problems, you could write that as 1/4 times. There's lots of ways to do this. But sometimes it's better to just put it in the calculator the way you see it as opposed to trying to simplify the problem ahead of time. Hit enter, and you get 50. By not rounding, I got an exact answer. It means that at time equals 0, there were 50 bacteria. This experiment started with a population of 50 bacteria. Compounding interest continuously. This was your formula from pre-calculus. All we did is change it so that the interest is compounded continuously. We've done enough problems like this in pre-calculus. You can check out the notes from pre-calc or from honors math analysis if you'd like. I'm not going to spend any time on this problem. Just remember this formula. It's the same formula. The final amount equals the initial amount, which is called principal in economics. E, they use R, we usually use K, and time is T. It's the same formula with different letters. So let's go to something we've not done. You may have done this in a chemistry class somewhere. This is the formula that you see a lot. I don't like the negative here, and I'll tell you why I don't like the negative. We know that K is going to be negative, so there's no point in putting a negative there. It's more confusing. So just use your original formula. Okay? Half-life, something you've discussed in chemistry, is the time required for the material to decay. Half of it. Here's a formula to find half-life. You could also use this formula, meaning that half of your original amount is left from your original amount. This formula is much easier to use, so this is the one we're going to use. Why is K negative? Because we know that we're going to get a negative answer for K. We know that since it's decaying, the rate will be negative, so we're going to make it back into a positive. Let's try a problem. After 3 days, polonium-210 has suffered radioactive decay so that there was only 58% of the original sample. Find the half-life. It didn't tell me a final amount or an original amount other than 58% of it was left. So I can say that 0.58 was left of 1 whatever, 1 gram, 1 ounce, 1 pound, 1 ton, it doesn't matter, 58% of it is left. Okay? So I know my final amount and my initial amount. E is still E. It does not tell me the rate, but the time is 3 days. Let's solve this problem. I'm going to take a natural log of both sides, so natural log of 0.58 equals the E and the natural log will cancel out, so it's just K times 3, or 3K. So K equals natural log of 0.58 over 3. Again, you can approximate this if you want to, in case you're curious. It's about negative 0.182. But I really don't care. I don't want to approximate it. I want to use as close to the exact answer as possible. So now I know that the half-life is natural log of 2 over K. But I want it to be a positive K, so I'm going to make it negative K. So it's going to be natural log of 2 over negative natural log of 0.58 divided by 3. And again, your calculator will do this for you. I'm not going to type it in this time. You guys know how to use the bar. This will give you an answer that is an approximate 3.8174 days. That's approximately the half-life of this substance, which makes sense. After 3 days, we're almost to 50%, so it needs to be a little bit more than 3 days. The only thing you really need to know here is the half-life formula. And truth be told, you don't even need to know that. If you know what K is, you could go back to the original problem and say half the original amount, E, K is natural log of 0.58 over 3 T. And you could solve for T that way. By taking a natural log of both sides, you'd have natural log of 0.5 equals, the E and the natural log will cancel out, so it's natural log of 0.58 over 3 T. So T equals, instead of dividing this fraction, I'm going to multiply by its reciprocal, so natural log of 0.5 times 3 over the natural log of 0.58. And it will give you the same answer. So even if you do not remember the formula for half-life, you can still use some common sense and figure it out. The third way we're going to use exponential growth or decay in a new way is Newton's law of cooling. This formula allows us to figure out how fast something cools based on the room temperature. Obviously, something is not going to cool down below room temperature. If we have soup that starts out at 150 degrees Fahrenheit and the room is 70 degrees Fahrenheit, the soup will cool to that 70 degrees eventually. It'll never go below. So here's a formula. This is your final temperature. This is your starting temperature. These two things are your room temperature. K in this problem, sometimes you will see it written as a negative. I don't like that. I like to just say KT, so it's all the same formula. But remember, K is going to end up being a negative number here. Why is it going to be a negative number? Because we're decaying, we're cooling, we're losing value. Suppose a cup of soup cooled from 90 degrees to 60 degrees in 10 minutes in a room that is 20 degrees. So let's use this information and let's write what we can. So, our formula says the final amount minus the room temperature equals the initial amount minus the room temperature, e to the KT. So let's plug in what we know. The final amount is 60. The room temperature is 20. The starting amount was 90. Room temperature is still 20. E to the K, and T is 10 minutes. Cleaning this up a little bit, you get 40 equals 70. E to the 10K. Divide, you get 4/7 equals E to the 10K. Take a natural log of both sides. You get natural log of 4/7 equals 10K. You'll get K equals natural log of 4/7 over 10. You can approximate that if you would like. I'm not going to approximate it. I want as close to the correct answer as possible. So, how much longer, not how long, but how much longer will it take for the soup to reach 35? So what's happened? Is my starting temperature 90 or 60? Well, since I want to know how much longer it's going to take, my starting temperature is now 60. And my final temperature will be 35. So 35 minus 20, that's my final temperature, that's my room temperature, I'm now starting from the 60 degrees it's cooled to. E to the natural log of 4/7 over 10 t. There's only one variable here I can't solve for. Or I don't know, I can solve for it. So let's clean this up. 15 equals 40 e to the natural log of 4/7 over 10 t. A little bit more work will show you that 3/8 equals e to the natural log of 4/7 over 10 t. Let's take a natural log of both sides. So then we'll have natural log of 3/8 equals natural log of 4/7 over 10 t. Instead of dividing by a fraction, I'm going to multiply by the reciprocal, so 3/8 times 10 over natural log of 4/7. Again, you can type all that in the calculator, and if you do that, you'll get an approximation. It will take an additional 17.527 minutes. So it took 10 minutes to cool from 90 to 60, but it's going to take 17.527 minutes to cool the rest. This section is very formula heavy. A lot of it has to do with exponentials and logs. But what's the fundamental calculus concept behind exponential growth and decay? That unlike other things which change based on the time, this formula, which you need to know, is a differential equation that says the time changes based on a rate times the population, not the rate times the time.